message is perfectly simple.
Hello, Avon High School. ACE College Algebra 2 students, Mr. Record coming at you again with another exciting video about ellipses. This is the second video in the series that covers our Unit 13, and we'll be doing all of the problems pretty much on page 2 of the notes that lead up to example number 1. If you watched the last video, you started to kind of get a little bit of a feel for what's going on with an ellipse, and we're going to take a look more in depth at the equations of ellipse here. So on the top of page 2, you were asked to study the equations and the graphs of the two ellipses below and see if you can determine the connection between them. Well, when you take a look at the two graphs, you find that they are sort of roundish in nature, but they certainly don't look like circles. And they each have centers, and it really seems to be very, I think, obvious what the connection is between the center and the equations, or at least I hope it seems somewhat obvious, in that when you look at this first ellipse and knowing that the center is -2, 3, you could probably extract those values once again like you did in the circle's center radius form by just taking a look at the values that are inside of the parentheses. And the same thing applies to the second ellipse, which has a center of 3, -1. We're going to pull those together in the same fashion. All right, now if you take a look at what other things that we see, well, there's obviously got to be some kind of a procedure that we could use to figure out sort of the elongation, how long the ellipse is in one direction, perhaps how long it is or wide it is going to be in the other direction. And if you look at these two ellipses, they're a little different in that this guy here on the left seems to kind of be longer in a vertical fashion, whereas the guy on the right seems to be longer in a horizontal fashion. So all of those things are going to be addressed in this video. Now, if you take a look at the first equation, this is a very special equation. This is an equation that's written in our center form that we can extract the center from, but we can also extract some other information. And it basically comes down to this. If you have your ellipse set equal to 1, and that's what your goal is going to be, then the square root of the denominator of the y fraction is going to tell you how far you count from the center in the vertical directions. So we count 4 each way because the square root of 16 is 4. If you take a look at the denominator of the x and take its square root, 2 in this case, that's how far you would count in the horizontal direction. And once you do that, you've got your equation, you've got the information, I should say, to graph the ellipse. Now, the second ellipse is a little bit trickier because of the fact that it does not have that set equal to 1 characteristic. But that's not very difficult to do, because if we divide both sides by 4, right, you would want to divide by the larger multiple of the two numbers that are in front, in this case 4, we would have, let me rephrase that. You don't want to divide by 4. You're going to divide by 100. Apologize for that. I was thinking about something completely different. Yes, we want to divide by 100 because, again, our goal is to achieve a 1 in that spot. So I'm going to write that information up above because I am running out of room. So you'd have x minus 3 squared over 50 plus y plus 1 squared over 25 equal to 1. And then from this point, we could look at the denominator of the y, take its square root, and that's how far we would count, 1, 2, 3, 4, 5, in order to get our other points up above. And we can see that if we apply that 5 downward, 1, 2, 3, 4, 5, we're going to be able to get the other points on our ellipse. Now, unfortunately, when we look at this number here, the 50, it doesn't have a very nice square root. In fact, the square root of 50 is probably just a smidge bigger than 7. But if we were to count along this major axis, 1, 2, 3, 4, 5, 6, 7, it's really 7 and just a smidge more to find those 2 points, although it's kind of difficult to tell given the size of these particular small grid boxes. But rest assured that the length of that half side of that major axis is going to be the square root of 50. So I think that's kind of going to get the ball rolling a little bit so that we can do some of these exercises. Now you are asked here, how is the graph of an ellipse different from the graph of a circle? If this is information that you'd like to put in your notes, you're welcome to like pause the video and paraphrase what I say, but it basically boils down to the fact that the values that you see in the denominators are going to be different. In turn, that also applies to this form. Values that you would see in front of the variables are different. Had those values been the same, you would be looking at a circle. Let's face it, in the left-hand side graph, if 16 were the two denominators, then we would have counted out 4 blocks in the x direction from the vertex, as well as 4 blocks in the y direction, and then you can see that we would have probably something that was a lot more circular. Right? Now, it's also going to ask, how is this difference noted in the equation of ellipse versus an equation of a circle? And that's exactly the idea about the coefficients and or the denominators being different from each other. Let's go ahead and take a look at our first example. You're asked to identify the following characteristics of the graph of this particular equation, and it has been pictured below. So most of this example is going to outline some vocabulary again. First step, find the coordinates of the vertices. Well, the vertices, you remember, are the 2 points on the ellipse that are farthest from each other along a line that passes through the center. So that would be this very top point and this very bottom point. Now, of course, we can just look at the graph and say, oh, this ellipse has a point up here at -2, 7. So we could write him down. And it has a point down there at the bottom, as you can probably see, of -2, -1. But if we pretend just momentarily that there was no graph given to us in this problem, what we could have done is deduce the fact that the center of the ellipse would have been at -2, +3, and then knowing that the 16 is going to be some number that needs to be square rooted to get 4, we would have to take that 4 and add it to the 3. That's going to give us the 7, and then subtract 3 minus 4, and that's going to give us the -1. And then we could come up with our vertices that way. You would do something very similar to find the co-vertices if you weren't given the graph. Okay. So I'm going to back up and I'm going to say, hey, we were given the graph. Let's go ahead and use it to find these two guys. We end up with 0, 3. Doesn't matter what order you write these in. 0, 3 and -4, 3. And as I was saying earlier, you could still find those if you were never given the graph, because all you've got to do is know that the x-coordinate of the center was -2, and you would have to take this 4 and add 2 to the -2, and then subtract 2 from -2 to get the 2 new x values. The y-coordinate would stay the same. So there's our vertices and co-vertices. The length of the major and minor axis are typically going to be very easy, especially if you're given the sketch of the graph. The major axis is, actually let's do the minor axis first, it's listed first. It's just the smaller of those two axes. In this case, the distance all the way across is going to be a 4. Right? Basically what you would do is take the square root of the smaller number and double it. It is only a coincidence that that number is that denominator 4, so don't rely on that all the time. And then for the length of the major axis, you're talking about the distance all the way from the top of the ellipse to the bottom, which you can probably count to be 8 blocks. How would one be able to figure that out without seeing the graph? Again, you would square root this larger number, getting a 4, and double it. Now, all of that's pretty easy. Hopefully you're not falling asleep, because the foci is by far and away the trickiest thing to find. And if you've watched the last video, you may have remembered that we've come up with sort of a formula to find this. Now, the foci, remember, are points that are located somewhere along the major axis inside of the ellipse. And I know these two foci are somewhere in these two areas here, but it's not important that you necessarily sketch them prior to finding them. But the formula that we came up with basically says is you take half of the minor axis, which in this case would be 2. So you're just basically talking about a distance like that of 2. And we're going to square him. So we're going to use the Pythagorean Theorem as we pointed out in the last video. And we're going to add that to a value that I'm going to call f squared. And the f squared is going to be this distance here. That would be the distance from your center to that foci. Well, obviously we know the Pythagorean Theorem says that that distance is going to, the sum of the squares of that distance is going to equal this guy, right? Which, you know, we could call hypotenuse squared temporarily. But the situation is that that's not going to be very helpful to us. And what's extremely important to realize is that we found out that this distance, this hypotenuse distance, happens to be, if this will let me do this, the same thing as, wait for it, yep, that distance right there, which is half of the length of the major axis. So we don't need this hypotenuse squared stuff anymore. Instead, we can just say that this is equivalent to 4 squared. And that becomes extremely helpful because now we can easily solve for the f. So if we do that, we would have f squared equaling 16 minus 4. Of course, that means f squared is 12. F would be the square root of 12. Notice we will not take the plus or minus into consideration because we're talking about a distance here. All right, I would suggest that you reduce in simplest form any square root expression so that you're better off matching some multiple choice problems. And then you're not quite done because I didn't ask you to find this value f. I want coordinates of foci. So what that's going to mean that you're going to do here is know that these two coordinates that I'm circling now, each are going to lie along that major axis, which means they're all going to have the same x coordinate, -2. That's not going to change. It's the y coordinate that we're after. And if we just simply take this idea that the center is where we're going to start, which is +3, we just simply need to add the 2 square root of 3 to get the foci that's above, and then we'll subtract 2 square root of, that should be square root of 3, I apologize. We'll subtract 2 square root of 3 to get the foci that's below. So basically, that's where these 2 points are located. And I think if you were to plug these into a calculator, you would very likely see that they seem fairly reasonable. So I'm going to close out this video with example 1, and in the future, we're going to take a look at some other examples where you are going to be given an equation right from the very beginning, and one of the things obviously is for you to sketch the graph, but you're also going to identify and label coordinates of foci, which is obviously going to be the thing that you're going to need to practice the most since it's probably the trickiest. But anyway, I hope this helps, and I will see you